All right. What I'd like to do now is help you through some of this information on correlation and regression. Make sure that both sections of the class are on the same page. So I'm going to start off with a quick review of some of the slides from Chapter 4. You'll also want to pull out, if you would, the correlation and regression packet that I distributed in class, because I'll bounce between the two of these as I take you through a series of videos to get you through the rest of the content on this chapter. So just real quickly, just to make sure everybody's on the same page, I'm going to turn to this slide where you see what I've done is I've highlighted for you that there are two major attributes of the Pearson product moment correlation coefficient, or the Pearson R. The Pearson R can range from a -1 to +1, and when we interpret the R, there are two things that need to be in the interpretation. That is the strength of the correlation as well as the direction. So this should be review, so I'll go very quickly by reviewing the fact that the strength is really a matter of how close these points fall to the line. The closer the points are to the line of best fit, that's going to create for a Pearson R of close to +1 or -1. And the strength of the R essentially is, we look at the absolute value, the magnitude of the correlation, and that gives us an idea of the strength. I'm going to go through the next slide and show you that there also is the attribute of the R, which is the direction. As you increase on your X variable, you also have an increase in the Y variable. We see that there's what we call positive or direct relationship. And here we see that the amount of time spent training is negatively or inversely related to runtime. And you can see that by the direction of the slope. The direction of the slope is the same as the direction of the correlation coefficient. So a positive or direct relationship is when high scores on one measure are associated with high scores on the other measure. And a negative or indirect relationship is when high scores on one measure are associated with low scores on the other measure. So what's the nature of this relationship? I hope all of you can see that this is a direct or positive relationship between pull-ups and chin-ups, as would be expected. The more pull-ups that you're able to do on the x-axis, the greater of the number of chin-ups you're also able to complete. Here we have an inverse or negative relationship, and this is the relationship between body weight, which is on the x-axis. We call that x-axis variable, and you should absolutely know this. The predictor or the independent variable, it's the presumed cause, and then you can see the corresponding scores here for the presumed outcome, which is your y variable. We call this the dependent or outcome variable, or the response or criterion variable. So different names for these, but we're essentially looking at the relationship, and here we see that negative or inverse relationship between body weight and the number of pull-ups you're able to do. It's also possible that there's not a really good linear relationship that describes what we see in terms of a relationship between X and Y. And in this particular slide, we see that there is really no condensing of these points around a line of best fit. So in this instance, we would say that the correlation is equal to 0. So once again, two major attributes with regard to the interpretation of correlation: the strength and the magnitude, as well as the direction. The strength and the magnitude, how strong we say a correlation is, really is kind of arbitrary, in that some correlations are strong, some are weak. I think it's best to use the interpretation sheet that I've posted on Moodle for you, which give you an idea, for example, that a correlation of plus 0.7, a correlation of minus 0.7 would both be considered strong or high correlations, whereas we get down to the 0.3 range, those are lower correlations. They're weaker, whether that is negative or positive in direction. And then obviously we have to specify the direction as well. So what we're going to see now, if we go to this next slide, that there's a question here: how would you interpret an R equal 0.85 between pull-ups and push-ups for a group of male cadets? I hope that you will refer to the handout that I've posted. I've worked really hard on this so that you could have a nice interpretation. But the way that I would describe this is that there is a strong positive relationship between pull-ups and push-ups in this group of male cadets. Whereas when we see a Pearson R of negative 0.3 between the time on a balance test and the likelihood of falling, we would refer to this as a weak inverse or a weak negative correlation between these two variables. So where we're going to go with this in the next video unit is we'll talk a little bit about what is the possible range of the correlation coefficient. I think we've already mentioned it goes from -1 to a +1. We're going to talk about the fact that we can misinterpret a Pearson correlation. We can misinterpret a graphic relationship, and we'll talk about the importance of looking at the graphic relationship as well as the Pearson R in order to interpret what's going on with a possible relationship between two variables. We'll take a look at what's called the correlation matrix, which is really a bunch of intercorrelations between a number of variables. You want to memorize the idea that correlation does not equal causation, and we will talk about some ways of determining how good a correlation is. One of the ways to do that is to look at what we call the coefficient of determination. Please memorize that term. It's the coefficient of determination. It's the R squared. We're going to finish up our discussion with prediction and the errors that are involved in prediction, the most famous of which is called the standard error of the estimate, or what we're going to abbreviate as SEE. So before we go on, what I'd like to do is I would actually like to refer back now to this correlation and regression packet. On page 2, you see that we've collected some raw data, in this case on 10 different subjects. And I'd like to focus in for just a minute and see that we can have measures for each of these 10 subjects on body weight. We can have measures for each of these 10 subjects on the number of pull-ups that they're able to do. And I've highlighted for you for subject number 3, he is 140 pounds and he's able to do 12 pull-ups. One way in which we can look at the relationship between how all of these subjects scored with regard to their body weight and the corresponding number of pull-ups is by producing a graph. You should know that the graphs are called scattergrams or scattergraphs, and we can see now as we look at these points that there is a dot or a point for each person on each of the two variables. So I would imagine that if we looked at the table above, you'd see a subject who weighed 130 pounds, who did, it looks like, approximately 7 pull-ups. Whereas we had a subject who weighed 140 pounds, who did 12 pull-ups. His point is depicted right here. Okay? We also see that we can draw a linear relationship between these two variables that tries to minimize the distance of these points to the line. We call this the line of best fit. It also is called the prediction or regression line. And you'll see here that in the case of subject number 3, he was 140 pounds. And based on the data from the group, we would predict, based on what happens with this line, that he would do close to 8 pull-ups. But you can see he kind of surprised us all. He actually did 12 pull-ups. So you can see that the error in his particular score, the error in a score for a single individual, is their actual score minus the predicted score, which gives us an error of about 4.03 pull-ups. All right, coming back now to the packet, I want to remind you that these correlations are extremely important in our field, and it's important that you know how to move ahead with the interpreting these correlations, because there are many practical applications. One of them we've already talked about, and next to this one you might want to write the word redundancy. Redundancy. We know that we have 2 measures perhaps in which are highly related in a multiple test battery. If these 2 measures are highly correlated or highly related, we may be able to get by with only doing one of these measures in the test battery, because essentially they're telling us the same thing. So this is the issue of redundancy, and one of the things we want to do, obviously, is respect the time of our staff and our clients and minimize doing multiple tests that are really measuring the same thing. A second practical application or use of this correlation and prediction material that we're learning right now is that the cool thing is if we find that something is highly related to performance, for instance, then we can find out that it would be worthwhile, most probably, to train the person to improve that variable, with the idea that if you improve that predictor variable, you then would improve the outcome or the criterion variable, which is performance in this case. A third reason that we like these correlation and prediction mathematics and applications is because there may be the possibility for simpler, cheaper, less invasive tests that you're able to do. If two tests are highly correlated, for goodness sakes, if one costs less and gives you essentially the same information, you'll be able to go with the simpler, cheaper version. A fourth purpose for correlation and regression has to do with risk assessment. And next to this, you might want to write in big letters, risk factors. Risk factors are factors that are associated, for example, with disease. And if we know that there is a risk factor of blood pressure that's associated with your risk of stroke, potentially we can estimate your risk of stroke and lower your blood pressure in the hopes that it consequently will lower your risk of stroke. So if you click onto any of these links, which I encourage you to do as you're reading and studying this packet, you can see that you can click onto this link and find out your 10-year risk of having a heart attack because of our knowledge of the correlation between various variables and your risk of this particular health outcome. And then finally, we're going to talk about validity and reliability coefficients in our next units in this class. And many of these coefficients are based on the Pearson R, although there are better ways of looking at validity and reliability. The importance here is that you can relate two numbers, and you can do that with the Pearson R. It's especially going to be important when we look at what we call validity coefficients. So I've already mentioned to you that in addition to the scattergrams and scatter plots that we've been talking about, we also are able to mathematically determine what is the value for what we call the Pearson R, and the computational formula is shown for you here. If you are not able to very quickly come up with a Pearson R with your two-variable calculator, please see Andre. I'm sure he's willing to help you with this. My calculator is the very basic calculator that does two variables, and my calculator will spit out for me the n. It will spit out for me the sum of the x times y's, the sum of the x's, the sum of the y's. It will also spit out these latter two sums so that we can plug everything we need into this formula. The only one I have to calculate is once I get the sum of the x or the sum of the y, I simply square them and I can put them into the appropriate point in the equation as well. Now remember that the Pearson R, or the Pearson product moment correlation coefficient, is what we call a parametric statistic. It's appropriate for normally distributed data that is of interval and ratio level. If we have ordinal level data, which would be the case with ranks, we're going to use what is called the Spearman's rho. Another name for that is the rank order correlation coefficient. This material at the top of page 4 now is actually a repeat of what we've just reviewed in the slides. So I'll take a minute to just go over it. You'll be able to read it in detail and make sure that you understand the concepts. If you remember, there are two aspects of the correlation, both direction and strength. A positive or direct relationship is when high scores on one variable are paired with high scores on the other variable, and negative or indirect relationships is when low values of one variable are paired with high values of the other variable. So there's some reasons for negative correlations, and you should know those reasons. Certainly I will ask that when it comes around time for quizzes and exams on this material, but you've already reviewed that, and it's shown in your textbook as well. I mentioned that there can be no linear relationship between variables, and we see that in this last example here where we take a look at the height in inches and the life expectancy. There's pretty much zero correlation between the two. Tall people, short people, moderate people. Doesn't seem to be a strong relationship between life expectancy and height. There is, on the other hand, a fairly strong inverse relationship between how many years you've been heavily smoking and your life expectancy. As expected, this is a negative or indirect relationship. And the positive relationship is shown here between your height and your weight. Taller people tend to weigh more. Taller people tend to weigh more. I've already reviewed for you one aspect of the correlation coefficient is the strength or the magnitude. And we want to take a look at how close the Pearson R is to either -1 or 1. So we're interested in looking at the absolute value of that correlation. The stronger the relationship, the closer these points are to the line, that would be a great example of a strong relationship, whether that is inverse or direct. Inverse or direct. What matters is how close the points are to the line of best fit in determining the strength of a correlation. Okay? We're going to be talking about in just a second what are some of the factors that influence the correlation coefficient. So I'll minimize this. I'll refer us back to our handout packet that we're reviewing in Chapter 4, and I'd like to go over that before we turn back to the handout packet. So there are, and you read about these in our textbook, factors that can influence the Pearson R. And that is, we can be misled by looking at the Pearson R alone in trying to understand if there's a relationship between variables. We might think there is no relationship between variables, yet there may be, and we may not be able to see that unless we actually produce the scattergram or the scatter graph that really illustrates what's going on. Similarly, a scattergram or scatter plot alone can be misleading. So we always want to look at the Pearson product moment correlation coefficient. We want to look at that R value before we try to interpret and understand what's going on. So this whole next section really falls under the guise of some of the limitations of the Pearson R. There are two main limitations that are discussed in your textbook. You have to memorize and understand these limitations. They're very important so that you don't get misled. The first one has to do with restricted range or variability of scores, and the second one has to do with the idea that the Pearson R only enables you to look at a linear relationship. So when you have variables perhaps that are curvilinearly related, or it's an exponential function, you may be misled by looking at the Pearson R alone. So let's go through this, and the next 6 slides or so really deal with this first limitation or this first factor that can influence what we see with the Pearson R. And that has to do with restricted range or variability of the scores. So let's take a look at that. The next 6 slides deal with that. I'll run through these fairly quickly. If you take a look on this particular slide, you actually see a scatter plot which illustrates some of the data from my dissertation. I was very much interested in economy, which is another word for efficiency in race walking in some of our national team athletes and some of our Olympic athletes. And I was wanting to see whether how efficient they were was related to their race walking performance. Well, I measured the national team, I measured the Olympic team, essentially, and looked at how economical these race walkers were. And what you see here, if this end of the scale is high on economy or high on efficiency, you can see that the group of race walkers that I looked at was very homogeneous. There was a restriction in the range of the values. All of the athletes, in order to qualify for the Olympics and the national team, had to have very high economy. They also were very high in regard to their race walking performance. These were some of the fastest race walkers in the world at the time. And so we have a very homogeneous group. It's not spread out. And if you were to see how close these points are to the line, you see that there's doesn't seem to be a positive or negative relationship here between how economical these women were and their race walk performance. And the reason is this data suffers from a limitation called restriction of range. The group is very homogeneous with regard to their economy. They're very homogeneous with regard to their race walk performance, and so that the actual correlation between these two variables that I hypothesized were going to be key in my research was actually R equals 0.02, okay? So there was very low, in fact, there was zero correlation pretty much between how economical these women were and how well they performed in race walking. There were other physiological variables, though, that, and this one is the velocity at which they had the onset of blood lactate accumulation. That was a very good predictor of race walking performance. This correlation was 0.85. It's not shown in this slide, okay? So I want to illustrate one of the major limitations of the Pearson R, and one of the reasons you may have a very low correlation is because you have a very homogeneous group on either one or both of the variables. You've restricted the range, and the correlation tends to be very low. If, on the other hand, instead of just measuring, as I'm showing you here on this graphic, the Olympic and national caliber athletes, instead I had looked at the economy or efficiency of race walking over a spectrum of athletes, perhaps recreational, including some of the recreational race walkers, I would have seen a much higher correlation, perhaps in the range of 0.7 or 0.8, in that race walkers that are more economical, in fact, have greater race walking performance. Those that are less economical have poor race walking performance. So this is a more heterogeneous group. That brings up the value for the Pearson R. I definitely would have seen a decent correlation had I looked across a wider spectrum of race walk performance levels. So here's an analogous situation. What you're going to see here is that, and I'm going to reiterate this, that the R is going to be smaller for a homogeneous group where there's small variance, small range, as compared to a heterogeneous group, okay? So we go across the spectrum, and what you see is an inflation of the R, a much stronger correlation, a much stronger relationship. So now I'm going to show you kind of a similar situation. Once again, restriction of range. We only have a few scores. I don't know about you, but you look at this, and what would you guess is the correlation? I would guess it's pretty close to zero. But look what happens if we include a few of what we call the outliers. You include people in the extremes, and now, all of a sudden, you've massively inflated your Pearson product moment correlation coefficient, because now the data seems to fit a straight line quite nicely. So again, be careful when you interpret a Pearson R. When you include these extreme or outlier scores, you're going to end up with a much higher score than if you had not included these couple of scores down here in this extreme part of the range. Same thing here. Zero correlation when you have a single group up here in the corner. I would say that that Pearson R is very low. If, on the other hand, we were to include a second group, you see that this massively inflates the Pearson product moment correlation coefficient, or the Pearson R. Okay? So, those 6 slides, I could go back through them, but I'll let you do that on your own. Those 6 slides that I've just reviewed deal with the limitation of the Pearson R that have to do with the restriction of range. Whenever you restrict the range, whenever you have a homogeneous group, whenever you have a group without outliers, your Pearson R is going to be low. So be careful that you actually look at the picture or the scattergram before doing the interpretation. The second major limitation of the Pearson R is that you can be misled. If I were to look at this data that shows you the level of arousal from low to high, and over here on the y-axis we have performance in the sport, we see that there's the inverted U type of relationship. That is, low levels of arousal, low levels of performance. Moderate levels of arousal, very high performance, but too much arousal, too much anxiety, low performance on the part of the athlete. Is there a relationship between arousal and performance? Absolutely. But that relationship is curvilinear. So when we do the Pearson R, okay, there is no linear relationship between these variables. The R is going to be very close to 0. So please make sure you see that and that you understand the second limitation here of the Pearson R. And that is when you have a curvilinear relationship, your Pearson R is going to be very low. But there could be a relationship. It is just curvilinear and not linear. Okay? All right. Here is the other side to misinterpreting things. Here you see a plot, and when you look at what is the club head speed of a golf club, you would think that as the club head speed increases, you would see that the distance that the golf ball goes would be much greater. But when we look at this, you don't see that there's much of a relationship. In other words, it's not positive, it's not negative. I would suspect that this correlation would be near to 0. But now what I'm going to do is I'm going to change the scale on the y-axis. I'm going to show you the exact same data, but now I've spread these numbers out a bit, and here you can see that it appears as though there's a positive relationship, as we would expect, between club head speed and the distance that the ball travels. So, important point here. Look at the scatter plot, but be sure to also calculate the Pearson product moment correlation. When you do both together, you won't be misled by the Pearson R alone or by the scatter plot alone. Okay? Next point here has to do with what we call the correlation matrix. The correlation matrix is a view of many different correlations that are interrelated to each other. So what I want you to do right now is to see that you have here a number of different values that are highlighted for you in yellow. These are correlations of 1 or perfect correlations. This makes sense. If we take the whole group scores on VO2 and we relate them to that same group scores on VO2, we're going to have a perfect correlation. Anything correlated with itself is always going to be a perfect correlation. All right? Now, what is the correlation between VO2, and this would be VO2 max, and the number of steps taken? So what I do in this case is I can look across in the row that is steps. I come over here to the column that corresponds to VO2, and I see that that correlation is positive. The more steps that people take, the higher is their VO2 max, and that's probably a low to moderate correlation between these two variables. Okay? The next question says, if I had to predict the VO2 max using one of these variables, which one would we use? Well, I'm going to look down the column here, which indicates VO2 maxes, and I'm going to look for the correlation, which is the highest absolute value. While this is high, this is actually a stronger correlation, so that we see that we could actually predict VO2 max with a stronger correlation, less error, dots that are higher or closer to the line of best fit if we use body weight as the predictor. So if we had to predict VO2 max using one of these variables, the variable that I would use would be body weight. Let's take a minute. Let's go back to our handout packet. Let's review these concepts in the packet, and let's make sure that you understand them completely. I'm on page 5, and what you see here is a replication of what we've just talked about regarding some of the limitations of the Pearson R. These are factors that influence the correlation coefficient, and emphasize to us that we always need to look at the graphic. Here we see the first reason that's cited in your textbook. When we restrict the range, when we have a group that is very similar on a given parameter, when we have extreme scores or not extreme scores, this is one of the major factors that can influence the Pearson R. General rule, the more you restrict the range or the variance in the score, the less deviation, the more homogeneous, the more you exclude extreme scores, the lower the correlation is going to be. All right? Restrict the range, homogeneous group, you don't include outliers, your correlation is going to be lower than if you use extreme groups, if you use more heterogeneous or varied samples. Those kind of things will inflate your correlation coefficient. We already mentioned too that there's the curvilinear relationship. You can describe those relationships, only the Pearson R is not the way to do that. You would do that with some type of not linear regression, but what we call a polynomial regression equation that includes exponents. You guys get the idea. Here were my race walkers. When I included a more extreme variance on the groups, what I get is a higher correlation than simply looking within this very restricted range. Similarly, zero correlation here. You throw in a single outlier, and all of a sudden you can draw a line that would inflate the correlation if you're able to include an outlier. This is the curvilinear example. The correlation is zero. Doesn't mean there's no relationship. It just means that that relationship cannot be described by a straight line. And this is one of the classic examples. I would become familiar with it. As we get older, generally we get stronger, okay? Really, strength increases fairly linearly until we're about 35 years old. And then I'm sorry to tell you that as you get older, you're going to see a fairly steep decline that even accelerates in the latter years here. This is a relationship between age and strength, but it is not a linear relationship. Lastly, we see a little bit different picture of a correlation matrix in the I'm on the bottom of page 5 here, and I'm going to ask you a couple of questions that are like your homework assignment now. So if you'll look at that correlation matrix that's in front of us in our handout packet, what's the correlation between pull-up scores and mile run time? So here I could come over here, I could come across pull-up, and I could come over here and I'd see the correlation between pull-ups and mile run time is negative 0.52. There is a moderate inverse relationship between how many pull-ups you can do and how fast you run the mile, okay? You'll also notice that I could have come over here in the column that said pull-ups, come down here to mile run time, and I see that minus 0.52 correlation is going to be identical. Anything correlated to itself is going to be 1. And essentially, these two sides of the correlation matrix, the things up here and the things down here, are kind of flipped over images of the same data. Let's answer this next question. What is the correlation between sit and reach scores and pull-up scores? I'm going to come over here to the column that says sit and reach. I'm going to move down to the part where it says pull-ups, and I see there's an extremely weak positive relationship between sit and reach scores and pull-up scores. That Pearson R is equal to 0.14. And finally, what's the correlation of anything to itself? Your answer is always going to be 1. Your answer is always going to be 1. If you were asked, and this is questions in your homework, what would be, out of all of these different scores, the best predictor of your pull-up score? Okay, I'm looking in this column. I'm going to look down this column and I see that the highest absolute R value is this one for skin fold thickness. And so I would say that the single best predictor, based on the strongest correlation, is the relationship between skin fold and pull-up scores. Okay? So please check that out. Notice that the correlation is negative, but it's still the best predictor in that case. All right? I'm going to go back to the slides now, which are not here, but here. And I think I'll give you a little bit of break so you can read through. You should now be through slide number 30, and you should now have read through, thoroughly understood, and reviewed the first 5 pages of the handout packet. So I'm going to stop this here.